In this last section, we're going to look at general laminates, those that aren't necessarily symmetric. And we're going to, in this first part, just generate the equations we need to look at stress-strain relations and the relations between stress resultants and strains and curvatures. So far we've only looked at symmetric laminates. And the nice thing about doing that was we were able to look at the in-plane or extension behavior and the bending behavior independently. We said those were not coupled for symmetric laminates. But when you have a general laminate, that goes out the window, and so there can be coupling between all those modes, and so we have to be a little more general in our approach. So if you remember, we have stress resultants of both the stress resultants Nx, Ny, and Nxy, and the moment resultants Mx, My, and Mxy due to the stresses sigma x, sigma y, and the in-plane shear stress tau xy. All right, our definitions for those, if we integrated the stress over the thickness, then that was the resultant, the stress resultant in sub x. And similarly, if we looked at the stress times the distance away from the midplane, z, that was forming a moment, and so we integrate those over the thickness. That would be the definition of m sub x. And of course, we have similar definitions for the other stresses and stress resultants. If you remember our numbering scheme, when we looked at bending, we started at the top with layer 1 and went to layer capital N as being the number of layers. And so for each layer, we needed to know its top and bottom surface. So we numbered those starting at Z0 at the top, going to Zn at the bottom. So for that layer K, somewhere in the middle, its top surface would be Z of K minus 1, and bottom surface would be Z of K. And also remember that we measured Z from the midplane downward. So now let's look at our stress-strain results. For each layer, the stress we found to be equal to the total strain minus the free thermal strains, and so there are those stress-strain resultants in global coordinates. But the strain would be equal to the midplane strains plus the strains due to the curvatures. And so again, we're kind of combining what we had in section 6 when we looked at thermal stresses and what we have in section 5 when we looked at bending. So putting that all together, we can say that for each layer we can define the stresses this way as the global Q matrix, that is the Q bar matrix, times the strains, which is the midplane strains, the curvature, and then subtract off the free thermal strains. So that works for combined in-plane loading, bending, and temperature change. And with that in mind, we can apply those definitions for the stress resultants. For example, n sub x, we're just going to repeat those definitions right here. And now putting those into matrix form, we have the nx, ny, and nxy. And similarly for the moments. The only difference there, of course, is the presence of the z, the moment arm, if you will, in addition to the stresses. All right, so with that in mind, let's look at the n sub x, n sub y, and n sub xy, and substitute what we've just found for the stresses into here. We have a pretty long expression here, and again, it's an integral where we're integrating over the distance z, that is through the thickness, for each layer, and then summing those up for all the layers. So let's break that integral up into 3 pieces. And there's the third piece here. And we're doing this again just by looking at these separately instead of all together. Now, if you look at that first term right here, you might recognize this. This is essentially just the Q bar matrix times the thickness summed over all the layers, and that is the extensional stiffness, or the A matrix. Over here, we haven't had this one before, where we integrate z dz multiplied by the Q bar matrix and then sum those up. That's referred to as the B matrix. And finally down here, again, you might recognize this from the last section. Those are the thermal loadings, NXT, NYT, and NXYT. So those are the for the in-plane stress resultants. Now let's do a similar thing for the moment resultants. Again, there's the stress-strain response. So if we substitute that in, we end up with, once again, this integral that has 3 parts in it that we can break up separately. And so looking here, this is the same that we had earlier that we called the B matrix. Here where we have the integral of z squared dz times the q bar of every layer and sum those up, if you remember back from section 5, that is the bending stiffness matrix, or the D matrix. And you can see the form here looks similar to the temperature change resultants and thermal resultants rather, but with the presence of the Z in here, these are the moment thermal resultants, or the thermal moments, MXT, MYT, and MXYT. Okay, so you put all that together. Well, first of all, let's just break these out again and look at these definitions. We knew from before the A matrix is really just the Q bar matrix times the thickness summed over all the layers. And for the B matrix, we do that integral, and we have 1/2 zk squared minus zk minus 1 squared multiplied by the Q bar matrix and summed. And if you recall the D matrix, it's 1/3 zk cubed minus zk minus 1 cubed, which we said was similar to the area moment of inertia of each layer. Now for the thermal loads and moments, we did that for the thermal loads earlier, and saw that, for example, in XT, we looked at the first row of the Q bar matrix times the alpha terms of each layer, and then multiplied that by the thickness, zk minus 1, and then summed those up over all the layers and multiplied by the temperature change. So we're going to have a similar thing, of course, for the moment resultant. The only difference would be, now we were integrating z dz, so we end up with the 1/2 zk squared minus zk minus 1 squared for each of these. And of course, similar ones for NYT, NXYT, MYT, and MXYT. These are all listed in the summary pages as well. So here's our final result. That in the middle, we call that the ABD matrix. And so what that relates are the loadings, which include the in-plane loadings, NX, NY, NXY, the moment resultants, MX, MY, and MXY, and all the thermal loadings, both the thermal loadings NXT, NYT, NXYT, and the thermal moments MXT, MYT, and MXYT. So all of those together, and what we relate those to are the mid-plane strains, epsilon x, epsilon y, and gamma xy, with the little naught, meaning that those are the strains at the midplane, and the curvatures. Now if we take a look at that ABD matrix just a little bit more to understand it just a little better, we looked at the A matrix earlier, and we said that this A12 is a Poisson's ratio term, so it relates extension in one direction to extension in the other direction. The 1/6 and 2/6 terms are extension and shear. And remember, if we had a balanced laminate, then the plus and minus layers would cancel each other out. So those terms were always 0 if we had a balanced laminate. Now the entire B matrix, that relates extension to bending. So if we pull on a laminate, it may bend or twist, and all those terms were 0 for the symmetric laminate, which is why we could look at in-plane loading and bending separately if we had a symmetric laminate. The D matrix, again, we've looked at that before. We have something similar to the Poisson's ratio terms, D12, and we have some bend-twist coupling that can be present as well. So everything on the diagonal, remember, is direct. So strain in the x direction related to stress in the x direction, for example. Everything else is a coupling term. And so again, the biggest difference between doing isometric materials and doing composites is all this coupling behavior that can take place, especially in a non-symmetric laminate. So finally got through all of that, and that's the most probably rigorous part of this whole exercise. But next time we're going to do some examples, and we've got a spreadsheet set up to handle all of those nasty equations that we've just set up. But we'll look at a couple of examples and compare some symmetric and non-symmetric laminates.